Now let's talk about two uses of rotation matrices. Okay, the first use is what we've seen before, which is representing the relationship between two reference frames related to each other by rotations, and the same rotation matrix allows us to transform the representation of a vector from one reference frame to another. The other. So what do we mean by that? This is just a quick recall. So if we had two frames, frame 0, and we had this notation, let's say we have r 0 to 1 going from allowing us to go from 0 to 1, then we have both the coordinate axes. Well, the coordinate axes are related to each other in this manner. Okay, in fact, this is how we defined this rotation matrix. And then if you have some vector v, then its representation in frame 1 is related to its representation in frame 0 by this relationship. Okay, so representation of v in frame 1 is r 0 to 1. Its representation in frame 0. Okay, so that's the first use, which has to do with transformation of representations or transformation of coordinate frames. A second use is actual rotation of objects which include vectors. Okay. Okay, so what do we mean by that? Let's draw a picture. So let's say we have some coordinate frame. Not that it matters. So we have some coordinate frame 0, and we have some point P with the representation Rx, Ry, Rz in this coordinate frame, and then we, let's say, rotate let's say this point or this vector OP and the point P goes to some other point P dash, okay? So point P goes to P dash, and P dash has coordinates, let's say Rx dash, Ry dash, Rz dash in the same frame, okay? So let's write that down. Point P so Rx, Ry, Rz is the representation of point P in frame 0, and P dash is obtained by rotating so what we mean by representation of point P is basically this is OP, the vector represented in frame O, right? So P dash is obtained by rotating OP about an axis through O, let's say, and these coordinates Rx dash, Ry dash, Rz dash are basically the representation of OP dash in frame O still, right? So here we have two frames and we are representing the same vector. Here we have one frame, but the vector itself changes, okay? So that's the difference. So this is a representation of P dash in O, okay, or a frame 0. Okay, so what is the relationship between this and this? So we can call it Q, the rotation, let us call the rotation matrix that takes us P to P dash Q. If we want, we can put a subscript like that, but that's not necessary. In any case, we just have something like this, and what we're doing is just choosing to call this quantity, this transformation matrix, right? So that's what we're calling. If we want to write it in vector form, well, what we have written here is OP dash and then some tensor. Well, I guess we should say it's going to be the 3x3 matrix that represents a general tensor that achieves this rotation times OP vector, all represented in frame O. Or if you want to write it in sort of abstract form without worrying about the coordinate frame, we can write this as OP dash equals some rotation tensor. This is QP to P dash OP. Okay, so that's how you would write it sort of in an abstract manner without worrying about the coordinate frames in which we are presenting. But once you specify the coordinate frame for both OP dash and OP, Q gets fixed, or at least we can specify Q in those in the context of those coordinate frames. Of course, we don't. Q is not necessarily unique if all you know is that it takes some point P to P dash, but we can certainly find a Q that achieves that. In any case, we're calling such a Q, such a rotation matrix Q in this context. Now, what we want to do is see if we can find a conceptual relationship between rotation matrices that do things like this and rotation matrices that do things like this. Here, the rotation matrices allow transforming representations from one coordinate frame to another. Here, so we have two coordinate frames here, right? So we have, just to make clear the contrast, we have a coordinate frame like so, ex naught, ey naught, ez naught, and we have another coordinate frame ex1, ey1, ez1, and we have sort of some point P or V, or some vector V, and we can represent this vector in this coordinate frame or this coordinate frame, and the relationship between those things is what is represented in these kinds of relationships, right? Here, on the other hand, we have just a single representation, but the point sort of moves. Okay, can we find a relationship between rotation matrices that do this and rotation matrices that do this? And the answer is, of course, yes. Okay, so what is the relationship? So apply, so consider Q, the rotation matrix, P to P dash. Apply this rotation matrix to the unit vectors of 0 to get unit vectors of some new coordinate frame, let's call that B. So basically what we are saying is define EXB, EYB, EZB equals Q P to P dash. So that's a 3 by 3 matrix, right? EX naught, EY naught, EZ naught. Okay, so we define these new axes based on some rotation matrix that we define here. So what do we have here? We have some coordinate frame EX naught, EY naught, EZ naught, and then some other coordinate frame. Let's draw it in a different color. This EYB, EXB, EZB. Okay, so we have two coordinate frames like that, and we have some point R, point P, like so, that you can represent in either of these coordinate frames. Okay, so let's represent it first. Of course, we know that Rx, Ry, Rz is basically the representation of OP in frame 0. Fact, the representation of OP in frame 0 will be the same as the representation of OP dash in frame B. Okay, you can think about it. Think about why this should be true. It's because of the way B was constructed. So what we have is OP dash, the vector Rx EXB plus Ry EYB plus RZ EZB. Okay, and of course by definition this is equal to Rx X naught plus Ry dash EY naught plus RZ dash EZ naught EX naught EY naught EZ naught times Rx dash Ry dash RZ dash equals EXB EYB EZB times Rx Ry RZ. But of course EX EY EZ is this is basically equal to R 0 to B times EX naught EY naught EZ naught whole transpose, because this thing is a transpose of EXB EYB EZB written in this manner. So that's transpose times Rx Ry RZ. So we have EX naught EY naught EZ naught times equals exactly the same set of axes. And then recall AB transpose is B transpose A transpose. So that's what we are using here, times R O to B transpose Rx Ry RZ. You can sort of cancel these guys. So let's call this equation 2, and this guy is equation 1. This guy is equation 1. Comparing 1 and 2, we have the relationship Q P to P dash equals essentially this matrix R 0 to B transpose. Okay, so that's the key relationship. So we just essentially compare, like we said, this relationship and this relationship, and notice the equivalence of these two things. Okay, so that's the key result, if you will, key claim result, at least for in the context of this video. Now, what does this imply? So let's consider an example. Let's say we have some frame and we have some vector OP, and that vector gets converted to OP dash by a rotation angle theta about the z-axis. Okay, so let's say, so this is an example. Okay, go from P to P dash using a rotation by angle theta about axis EZ naught. Okay, now what is Q P to P dash, or this rotation? What is this rotation? Okay, what is the Q for this rotation? For this rotation, the idea is that Q is basically R0 to B transpose, where B is obtained by rotating frame 0 by angle theta about EZ naught. Okay, so that's the claim. But we know already what that rotation matrix is. R0 to B is given by, from our earlier derivations, it's cosine theta sine theta 0 minus sine theta cosine theta 0 0 0 1. So this rotation of objects by an angle theta about the EZ direction is actually that Q that takes P to P dash there is actually R0 to B transpose. So this is very important. This is actually cosine theta minus sine theta here, 0 sine theta cosine theta 0 0 0 1. So that's actually Q. Okay, so Q is this quantity. It's a transpose, right? So you should not naively assume that RO with respect to B is actually Q, rather it's RO with respect to B transpose. So the transformation that takes you from P to P dash is actually this matrix.